All right, we are live. Sanjeev, all yours.
Yeah, okay, hi guys. So today I'm going to talk on my research topic, that is deep reinforcement learning based controller for ship navigation. So first I'll briefly go through the overall process. So Rohit presented his pre-tech thesis like 2 months ago, and this is a
Sanjeev,
follow-up from there.
Sanjeev, just a second. You have another microphone which you can use, or you have to be louder a little bit. What's happening is the tail end of your voice always gets lapped up, and we are unable to hear that. So either you have to be a little louder, or you might want to try another microphone, whichever way you want.
Okay, I'll try to be louder.
All right.
Yeah, so first I'll talk about what we were trying previously, and then so I'll talk about how we have stimulated the ship dynamics. So and then I'll go through the RL setup for this problem. We have used TQNs, and then I'll go through the training process and the results that I have got, and then I'll talk about the performance of the controller in the presence of wind forces. So first, for any RL problem, you have the environment, the state, and the action. So here our environment is the how we are simulating the ship dynamics. So previously we were using the Apkowitz 3 degree of freedom model for the KCS vessel. And the problem with that was we were missing the rudder hydrodynamic coefficients. So as you can see, this turning circle, it is not converging at all. So it was not very practical. And so we discarded this one, and so now I'm using the MMG model as the simulation engine for the RL problem. So now I'll talk about how I'm modeling the mathematics using the MMG model. Okay, so this is the kinematics. So these are the global fixed axis, capital X and capital Y. Small x, small y are the body fixed coordinates. And beta is the drift angle. The heading angle is always measured from the positive x-axis in the global fixed frame, and the rudder towards the port side is taken positive. And since z-axis is downwards, so the yaw will be positive clockwise. Now I'll go through the equations of motions using the MMG model. So here the x, y, and n are the total forces, and this is the total surge force, the sway force, and n is the total yaw moment. And these are taken from the midship reference, and these equations u, v, and r, the velocities are measured from the center of gravity.
Here, X, Y, and Z are measured somewhere else.
Sir, come again.
Capital X, capital Y, and capital N, they are measured at about a different point.
Yeah, they are measured from the midship.
From the midship. All right.
Here, My, Mx, and Jz are the added masses and inertia. This is how the total forces and moment about the midship are calculated. It has the forces due to the hull, the rudder, and the propeller. So this is how the forces due to the hull are modeled in the MMG model. So in the usually in the Apkowitz model, we'll have hydrodynamic coefficients with respect to the surge and sway velocities, but it is different here in the MMG model. So the hydrodynamic coefficients are measured with respect to the drift angle beta and the yaw rate r. So in general, the MMG model is it captures the non-linearities much more clearly than the Apkowitz model. And this will be the forces due to the propeller. So this will be the thrust force basically. And this is how the rudder forces are modeled. So F1 here is the normal force acting on the rudder, and delta is the rudder angle. And these constants that you see here, TR, AH, XH are the interaction coefficients between the rudder and the propeller. And XR here is the position of the rudder from the midship, so it will be 0.5. As non-dimensionally, it will be 0.5. Any doubts still here? Okay, so now I'll talk about how in solving the equations of motions that I just talked about. So in this problem, the ship dynamics, it is solved as an initial value problem. So I'm discretizing the time to time steps of 0.3 seconds, and the max rudder rate is limited to 5 degree per second. So the rudder change is not instantaneous. And the rudder angle is the action that will be input from the RL agent. So that will be the commanded rudder angle, and the actual rudder angle, it won't change instantaneously. It will change at a maximum rate of 5 degree per second. The non-dimensional rudder time constant that we are using for the simulation is 0.1. So these were the turning circle results for the modeling that we talked about. So, as you can see in the MMG model, the turning circle won't be same for a starboard turn and a port side turn. So for a starboard turn, the turning circle diameter is 2.97 ship lengths. For port side turn, it is 2.74 ship lengths. This is the zigzag maneuver, 2020 zigzag maneuver for the model. So it has an overshoot of almost 20 degrees, as you can see here. Any doubts still here?
What's happening with the rudder angle here?
Yeah, so the rudder angle, it's a 20-20 zigzag maneuver. So as soon as the heading reaches 20 degrees, the rudder is reversed. And if it reaches minus 20 degrees, the rudder angle is changed to 20 degrees. So since we have a maximum rudder rate, so that's why this rudder is not sharp. You can see very smoothly as the turning rate is limited.
So there is a limitation on the rudder rate that it cannot be more than 5 degrees per second.
So 5 degrees per second.
Correct, right? And
yes.
But you also had some time constant in there, isn't it? 0.1.
Yes, sir.
How does that figure a role into this?
So this one, it's a reaction time for the rudder to take place. So this is non-dimensional here. So it roughly translates to 0.2 seconds for the 3-meter KCS model. So that value was chosen to be that was practically sufficient. So that was chosen.
So your rudder is actually depending on the applied rudder or the commanded rudder is what you are changing. But
yes,
the actual rudder changes some dynamics between the applied rudder, the commanded rudder. It depends through some differential equation, correct?
Yes, sir.
So what is that differential equation?
Okay, so that will be the rate of change of rudder will be the commanded rudder minus the actual delta C minus delta divided by the time step, that is 0.3 seconds. That will be the rudder
time step.
Yeah.
So where does T delta figure then?
No, I'm sorry. Delta C minus delta divided by T delta, the time step.
T delta, right? So T delta times delta dot is equal to delta C minus delta.
Yeah.
That's the first order system, so you kind of are assuming that there is a lag between when I ask the commanded rudder angle is provided to when the actual rudder will reach the commanded rudder. And yes, that time constant is 0.1 in this particular case. Right? But you still limit the maximum rudder rate, so you don't purely go by the differential equation. But
yeah, so if that rudder rate of change exceeds 5 degree per second, it is limited to this maximum. Yeah.
Correct. So if it exceeds that, then you limit it to 5 degrees per second. Otherwise, it is governed by it. So that's why when you look at your plot, it is straight in the middle portion. When it crosses over at 0, the rudder variation is linear. But then once it comes closer to the 20 degrees value, it kind of tapers in, right? That's because the commanded rudder is sitting at 20. But the actual rudder slowly inches towards it.
Yeah, that's right. So the actual rudder changes slowly, but at this point the commanded rudder will be minus 20 degrees.
Correct.
Slowly changes.
All right.
Sir, how does it capture the practical case?
How does this capture the
Practical case? Like, won't we put it to 20 degrees continuously at say 5 degrees per second?
No. It is put continuously here also. What he's saying is commanded is immediately shifting. So the moment your rate reaches, your angle reaches 20 degrees, your commanded value is immediately changing to minus 20 degrees. But the actual value of the rudder takes time to approach it. Is that making sense? In a zigzag maneuver, we are basically doing what we want to look at. Once the yaw angle reaches 20 degrees, we shift the rudder back to minus 20 degrees and we hold it there. So you are changing the commanded rudder angle to minus 20 degrees and holding it there. But the actual rudder doesn't move that fast. I can instantaneously change the rudder from minus 35 to plus 35 right at the next instant. But in reality, rudder can't respond that fast, isn't it?
Yeah.
So that effect is what he's trying to capture by that lag.
So delta here is the rudder angle, right?
Delta here represents the actual rudder angle.
Okay.
And delta C here will represent what is his commanded rudder angle. And if he had put that equation on that slide, it would have made things much more clear. So the equation
Maximum rudder rate change will be delta C minus delta divided by T delta. They're not included here. That is limited to 5 degrees per second.
So delta dot is equal to delta C minus delta by T delta.
Yeah, that's it.
Okay, that is the rate of change.
Yeah, and it is limited to 5 degrees per second, so it is not instantaneous.
Okay.
Okay, Avanish, you two had a question?
No, I just wanted to say that generally what happens when we apply this command to the rudder. So in program, when you say that you go to 0 to 20, it's like instantaneous, it's like a step input. But generally we don't do that. What we do is we use a rate limiter.
One second, Avanish. I am not able to very clearly hear you.
Okay. I'm saying that when in practical what we do is when we do experiments or when we really do in field, that when we say the program is saying that okay, you have to go from 0 to 20, it's like a step input. It means that it contains all the frequency which generally is not good for our system. We cannot excite our system which is all frequencies, infinite frequencies. So generally what we do is for our input, we generally put rate limiters. So let's say, for example, he has put it here that it has to go slowly to that commanded, the actual rudder and the command rudder should be like, in that case, when you put rate limiter, it will be same. So for example, I want to go at certain rate, so my input command will be also at that certain rate. So I won't be messing up with like exciting my system with infinite frequency.
So you want to say that the commanded rudder also should be smooth enough?
So yes, sir. So generally for that we use something called rate limiter. So or we can use the second order transfer function for reference signals. So that's how we do. So in practice we put the second order transfer function which takes our command input from 0 to desired at particular rate.
Correct. So if you put a second order system, your point is that you can actually control the rate as well as the actual displacement from moving very fast.
Yes.
Correct. And he is using only a first order system. So therefore, he has to take a maximum value of it so as to not to make it exceed the 5 degrees. But if you had a second order system, you could incorporate that also into the dynamics, is what you're saying. Am I right?
Yes.
Okay, all right. Okay, Sanjeev. So that's a point well noted. What his idea is that if you take a second order system, then what you are trying to limit your rudder rate, that also can be incorporated to be slow enough. Otherwise, now suddenly your rudder rate is maximum and you can't jump to 5 degrees per second rudder rate suddenly. So in your approach, your delta is continuous, but your delta dot may be not be differentiable. But if you use a second order system between your commanded rudder and your actual rudder, then that will also be differentiable in nature. And that's what is his point.
Oh, okay. So now I'll talk about the reinforcement learning setup for this problem. So I'll talk in brief about Q-learning. So Q-learning is a very basic RL algorithm. So it is not very practical because it works only with a discrete action space and a state space. And so it has to maintain a Q table containing the state action values. As the number of action and state space, as it increases, so notice that this becomes impossible to maintain. So it is maintained. So action state pair can be represented Q of S, okay? And Q, and so at a certain state S, there can be n actions possible, and the action that is chosen corresponds to the maximum Q value. So this Q value is quality value. So the optimal policy is chosen by the agent for which action the Q value is raised. So because this maintaining Q table becomes impossible, that's why we use neural network as a function approximator. So that is called deep Q learning.
So what is the Q value?
So that is called a quality value. So at a certain state, so since this is the action space is discrete, so there can be n actions, and for each action there is a value called the Q value.
So what does that Q value represent?
It represents quality value. So if an action has a higher Q value, so that will be more closer to the optimum policy to be chosen at that time stage. That's what it means.
Does it relate to the reward system in some way?
Yeah. So that action, if it chooses it, so it will accumulate more higher rewards.
Yeah, actually the Q value does have a direct mathematical relationship with the reward. It is the expected value of the reward, that if you take an action A from a state S, what is the expected reward that the agent would get? That's what the Q value represents. Okay. All right.
I'm very new to this. Can you please give me one example? I will just curious to understand this. So we have this state pair, action and state pair. So just wanted to do it. Is it like our delta, the rudder, and the heading style?
And did you get his question, Sanjeev?
Yeah, no, I was not able to hear clearly.
Avanish, can you repeat your question one more time?
I just wanted to understand this. So here our action and the state pair is like our rudder deflection and heading style or yaw rate are
correct.
Yeah. So right now the only action we are choosing is the commanded rudder angle, and the state observation state will come to that soon.
Okay.
He is going to talk about what is his state vector and what is the action states that he's choosing. He is going to cover that in just a bit.
Okay.
So the difference between Q learning and deep Q learning is a neural network is used as a function approximator, and the observation state is input to the network, and it outputs n Q values corresponding to each action. So this is the loss function that is used. This is called the TD error loss function. Yeah, so this is the observation state that I'm using for this problem. So I'm defining two quantities separately for this. So this is the coarse angle error and this is the sidetrack error. So I'll come soon to how I'm defining it. This is the distance between the between the current state and the current position and the destination point. And R is the array, and the action space has been discretized into three commanded ladder angles: -35, 0, and 35 degrees. So yeah, so this is how the problem looks like. So this is the destination point, this is the initial point. So the sidetrack error is the perpendicular distance between the line joining the initial and destination waypoints and the current position of the ship. And the coarse angle error is the difference in the heading angle of the ship and the desired heading angle. The desired heading angle will be the angle between initial and destination point from the positive x-axis. That's how coarse angle sidetrack errors are defined. And now, while training the episode, this is a single episode, so the aim of the ship model is to reach the destination point. And so we terminate the episode if it reaches the destination point. And radius of 0.5 ship lengths around the destination point, and that is chosen. The episode is successful if the ship comes into a radius of 0.5 ship lengths around the destination point, and it is also possible for the ship to miss the destination point and keep traveling. So that is just a waste of time. We want to stop that. So that is terminated. So I'll come to how we are terminating.
1 second. I think you go back one slide. Yeah. I think it was not very clear.
Okay.
Because I know your problem statement, it was very okay for me. I have a suspicion that it might not have been very clear. People, now is the time to ask the questions. You'll be able to clarify now and you will be able to understand from here.
Can you go back one more slide? I missed the loss function part.
I lost. Yeah, so this is called the TD error loss function. That theta represents the parameters of the neural network. So loss function is computed. This is the expected value of yi minus. So squared error, expected square error. Loss function is computed this way.
S and S dash is like next state, right? And S is
S is the current state, and A is the action that it takes. R is the reward that it attains for the specific action that it took, and S dash will be the succeeding state.
Okay.
And what is meant by function approximator? And so what are we approximating something? I didn't get that.
This is Q-learning basically. So here you have the states. So basically you have n states and n actions. Any discrete number of states and actions. So you will have to maintain a table for each state action pair, right? Basically.
I think that is the point which is very unclear as to what is the difference between Q-learning and deep Q-learning. That's where the question is actually hinting at.
Yeah. So as you have a large number of actions and you have a large number of actions in the action space and the state space, it becomes impossible to maintain a Q table. So that's why we use a neural network to approximate the function. Instead of the Q table, we use a neural network here. So the state is input to the neural network and the Q values are output from the network. So, is that clear?
It means that we cannot check each and every action since the actions are very large in number.
Yeah, you can. So this neural network outputs. So it outputs n Q values. So for corresponding to each action. For a certain state, if it takes this action from here, that corresponds to this Q value and so on. So outputs n Q values basically. And the one which has the highest Q value will be the optimal action to take.
Okay, so we are reducing the size of the, what you say? So are we reducing the size of the state space to the smaller? Is it like that?
No, we are not. No, we are not reducing the size of this state space. That is the same. I mean, neural networks can approximate the. I mean, it can represent the observation state much better than a linear function. That's why we use it.
Okay, I think. Can you go back one more slide? Okay. I think the basic difference between the Q-learning and the deep Q-learning, one has to understand. We appreciate why there is a need for replacing the Q-learning table by a deep Q-learning network. So what happens in a regular Q-learning is you are keeping track of what state you are in and what action you took, and then what is the reward which you got. So based on the reward you got, you're updating those Q values for all the different possible states of the vehicle. Okay, so in different states of the vehicle, the agent remembers that in this state I take that action and I got that reward. So an example might be that, suppose if you go back to your observation space, Sanjeev. So what's happening is that at every time step, the agent is actually given these 4 quantities. So it knows what is its cross-track error, side-track error, what is the course angle error, what is the distance to the destination waypoint, and what is the current yaw rate. Move to the next picture where you define these quantities. So when an agent is at this location, let's say, where he is showing in the picture, it knows what is the value of DC at that point, what is the value of the side error, and what is the distance to the destination, and then what is the current yaw rate of the vehicle. Based on these states, so that is what forms an observation state. So at every time step, it is being given, this observation state is being provided to the agent. And now generally in our simulation program, we are providing it to it because we know it mathematically. But in reality, when we are actually doing this on a real vehicle, you will be getting that information from your sensors. So let's say you have an IMU on board the vessel or a GPS on board the vessel, which will tell you, from that you will know what the precise position of the craft is, what was the initial waypoint you know, what was the destination waypoint you know. From that you can calculate what is the sidetrack error. Similarly, where am I headed right now? What is my current orientation and where should I have been heading if my position was this? That angle error you can also compute from the sensor information. So based on those sensor information, the craft knows these 4 things at every time step. Based on those 4 things it knows, it has to pick an action. And in his particular case, he is using what is called as a deep Q-learning, in which the action space is discrete, which means you have to choose between the 3 actions of applying a commanded rudder of -35, commanded rudder of +35, or putting the rudder at 0. Is the problem statement making sense now?
Yes, sir, yes.
Okay, so now you go back, Sanjeev, to your Q-learning slide. Yes.
So yeah, so here our states, as I defined, this is the observation state. So at each time step, the observation state is passed, and the agent learns to take one action, that is from the 3 rudder angles, it takes one rudder angle for the next time.
And every time an agent visits a particular state and it takes a certain action, it records it into a table of all the possible actions and states which you maintain. Now you can see that that becomes a tiring process when the number of states is increasing. Because you see, in this particular problem, the state vector is a continuous thing. If you look at what is the cross-track error or the side-track error, course angle error, the distance to the goal, what is the current yaw rate, these are not discretized quantities. They are continuously varying quantities. So if you wanted to keep a track of them in an actual table form, you will go crazy. Is that making sense?
Yes,
It's
yes,
a compounding problem. So the solution which deep Q learning offers is go to the deep Q learning slide. It's saying that you give me the state information which is continuous in nature, and I'll give you that if you chose action 1, what is the expected reward? If you chose action 2, what is the expected reward? If you chose action 3, what is the expected reward? I'll spit those values out. So a mapping from the state and an action to what is the expected reward, instead of maintaining a table, and then when you revisit that you are updating the table, instead of maintaining a table, I will be approximating it through a neural network. That's what it's essentially saying.
Yes, sir. Yes.
Okay, is that now making sense? Avanish, now I think it might be making more sense.
Yes, sir. Yeah, got your idea.
Okay, so now that's the point where he's saying that I'll replace that actual table with a neural network so that I can take advantage of the fact that I don't have to maintain such a big table, and I learn that behavior, that based on different states, what is my best reward strategy. That is what will be encoded in this deep neural network. Okay, I hope that has answered the questions which Aditya had.
Yes, sir. Yes.
Any other queries? Good discussion going on.
If there are no questions, I can continue. So on each a single episode, it starts from the initial point, and its goal is to reach the destination point. So, and the errors are kept track of at each time step, and the agent takes an action. So, and if the ship reaches the destination point, the episode is terminated and it is considered a successful episode. If not, if the ship if it crosses the destination point and it keeps traveling, we have to terminate it. So there's a termination condition if in case that happens. So imagine a perpendicular line dividing this plane, which passes through the destination point, and if the ship misses the destination, that is, if the distance between the destination point and the ship is greater than 0.5 ship lengths, and if it crosses this plane, it is terminated. So this is how it is mathematically represented. So that's the termination condition. And okay, epsilon 3D algorithm.
Can you go back one slide? All right. Here you have defined V1 vector and V2 vector. V2 is between the current location of the craft to the destination, correct?
Yes, sir.
And V1 is the initial waypoint to the final destination waypoint. What is the direction?
Yes, sir.
And the angle between those two is defined as phi.
Yeah.
Right? So in this particular location, the craft need not be traveling parallel to V1, does it? In order for phi to be 90?
No, not necessary. So
not necessary, right? It can travel at any angle as long as it is crossing over the plane which is perpendicular to this destination and initial waypoint connecting line and passing through the destination. That perpendicular line, if it is crossing and moving, you consider that the angle of phi is greater than pi by 2.
yes.
Right? And theta is your angle between?
Theta is the angle between this V2 vector and the ship velocity.
Okay, and if that is greater than 90 degrees, so when both these conditions are satisfied, that is when you presume that it is terminating the episode, correct?
Yeah, so if both these conditions are satisfied, it is very less likely to reach the destination from there on. That's why we terminated it.
Correct. So if in this particular position the velocity vector were more inward towards V1, then the episode will not be terminated.
Yeah, so let's say if it is on the perpendicular line and if it is oriented towards the destination point, then this theta angle will be close to 0. So there it can still reach the destination point, so it won't be terminated.
Correct. But whereas if that angle was 180 degrees and it was pointed right away from the destination,
then it is terminated. Yeah, if that is the case, it is not likely to reach the destination. So we terminate it.
Okay. Okay.
So now we'll talk about epsilon gradient algorithm. So every RL problem, it has a trade-off between exploration and exploitation. So what is exploration in an RL problem? So to learn all the possible actions from a possible state, it has to explore. So, and when it reaches, when it learns to gain the maximum rewards, then it tries to exploit the situation by getting maximum rewards. So that's why we use this epsilon gradient algorithm. So with the probability of epsilon, a random action is taken, and with the probability of 1 minus epsilon, the optimal action output by the agent is taken. So for this problem, so let's say I'm training for 10,000 episodes. At the start of the training process, the action taken will be totally random. So epsilon is 1 at the start, and it linearly decays throughout the training episode, such that at the end of the training process, it learns to take actions on its own.
So what is our value of epsilon as we taper down to less and less, more number of episodes are being trained?
Yeah, so right now I'm using epsilon to be linearly decaying. So at the start it is 1. So at the start of the training process, the action taken will be completely random. And let's say I'm training for 20,000 episodes, and around 10,000 episodes it becomes 0.5. So we're close to 0.5. So at that stage, what happens is it has probability of 0.5 to take a random action, and with the probability of 0.5, it takes the optimal action from the agent.
Okay. That might be the parameter which might cause your other problem which we were talking in the morning. Okay, but you will come to that. That might be the problem.
Okay, but it does not. It goes to 0. We've set it such that it goes to 0 like much before the training ends. So if I'm training for 20,000 episodes, epsilon goes to 0 around 16,000 episodes.
Yeah, I have a feeling it is decreasing very fast. See, it's a problem of between exploration and exploitation, isn't it? That if you are not giving it sufficient exploration time, and each problem has its own exploration time, that's the challenge with these sorts of problems. We don't know what is the exploration time to begin with. And if it has a larger exploration time which we have not given it, then it is reacting with a suboptimal solution. It has not found an optimal solution yet, as yet. That might explain some of the result which is going to come forward. Okay, anyway, we'll have a discussion more on that when you bring the result up.
Okay, so these are the 3 rewards that I'm using. So, sidetrack error reward. So we just define the sidetrack error there. So this is the sidetrack error reward. This is the course angle error reward. This is the distance reward. So at each time step, it gains all these 3 rewards, and that is input by the agent. And the total returns for an episode will be the discounted sum of the rewards at each time step. This is how the cross-track error reward and the course angle error reward varies. Now, so we have an experience replay buffer. So what this is exactly? So if we try to update the network by just using the previous time step, it will be biased. So what we do in the experience replay buffer, the memory of multiple previous episodes are stored. So this is called one single trajectory. At a single time step, what is the state, the action that it took, the reward, and the next state. So this is called a trajectory. And in the experience replay buffer, so if my replay buffer size is 10,000, let's say, and the memory of the previous 10,000 trajectories will be stored in the experience replay buffer. And while updating the network, some number of samples will be randomly chosen from the buffer to update the neural network. So it's the purpose of the replay buffer. And this is the network that I'm using as before.
Can you explain this experience replay buffer?
Yeah, okay. So the main purpose of this is to store the trajectories of the previous time steps as well. So this is called a trajectory. You understand what this is?
Yeah.
So yeah, so each time step has one trajectory. So if I'm saying the experience replay buffer is 10,000, then the previous 10,000 time steps, I mean the trajectories of the previous 10,000 time steps will be stored in the replay buffer. And if my sampling batch size is, let's say 100 samples are chosen from the replay buffer randomly for updating the neural network. Is it clear?
Okay, we choose randomly from that trajectory to train the neural network.
Yeah.
So what will happen if we don't do this?
So say we don't have a replay buffer for each update, it will just have the most recent trajectories. Right? So that way it will be biased. So this way the trajectories are reused also, and it is chosen by random. So there is no bias while updating it.
Okay.
And also that your waypoints are different in each trajectory.
Yes.
Because you may choose to go to the left side once, you may choose to go to the right side the next time. And if the right side is fully weighted and the left side is not weighted at all from the previous run, then you have lost that information for eternity. So you need to maintain some portion of the previous run and some portion of the new run in order to keep track of both of them. Now, Sanjeev, what was your size of the replay buffer in this particular example?
Yeah, I'll come to that. So it's like that.
I'm curious to find out that with respect. Okay, all right, 100,000 is your replay buffer size. And
so yeah, each episode had 160 time steps. So that's more than, I mean, it stores the memory of more than approximately the last 600 episodes.
Last 600 episodes it will store. Okay, and you're training for 20,000, 30,000 episodes, isn't it?
Yes, sir.
So at every time it only stores the last 600 episodes of the story. Okay, all right.
Okay, so this is the network that I'm using as the function approximator for the DQ. So there are two hidden layers, and the activation function is tanh. The replay buffer size is 100,000. The sampling batch size is 256. The number of episodes for which I'm training is 30,000. And the learning rate, I'm weighing it exponentially from 0.01 to 0.001.
One second. I think there may be an issue here which I should highlight. What are your Q values ranges?
I'm not sure the Q value ranges. So there's no activation function in the last layers.
So what's happening in the last layer?
So it can be any value. So it can be any real value.
No, it can be any. So it's a linear activation function. You simply add up whatever value comes out.
Yeah, I actually tried using a softmax activation for the final layer. It did not work.
No, you should never use a softmax for these sort of problems. Softmax is for classification problems. It's not for Q values. Okay, so, but you want to kind of keep but there is a limitation here. You realize that even if all the 64 units are +1 at the end, your maximum value, your Q value can reach is 64. Or it can reach a maximum value of -64. Correct?
Yes, sir.
But your reward structure goes all the way to some minus thousands, isn't it? When you look at your plots of reward versus epochs.
That is the total returns about the reward.
Correct. But individual returns, how much is the maximum are you getting? So
individual returns, so you can see core sample and cross-track rewards, that is less than distance reward. It is yeah, this is not bounded.
Yeah, this one is not bounded. You see, this is what will create problem. The problem will come that when the reward is very highly negative or when you are far away from the goal, it makes learning very difficult because your model can't reach those values of rewards ever. It cannot try to attain a -64 value ever. But whereas when you begin, the reward is actually much greater than -64 at that time. Am I making sense?
Yes.
But when you started off, let's say you're at the initial waypoint and the other waypoint is way far away, then the distance by 4, you're choosing somewhere in the lengths between 8 and...
Yeah. Yes, sir. So I'm choosing between 8 and 28. So maximum value, I mean, -7.
-7. Okay. -7, -8, -8.3 would be the maximum reward, which can be negative. Okay, all right. Okay, that seems to be okay then. It's not too bad.
Actually, I did try using a lesser magnitude for the distance reward. In that case, what happens is it takes a longer path than it's supposed to. So, I mean, that did not work. So, I think this factor of -0.25 is, I think that is good. So, that's why I did not change it.
Sanjeev, the previous slide, did you also try with value activation first?
I also tried with value activation in the intermediate layers. That also did not give good results.
Oh, okay. And how long does it take to train with this usually?
Yeah, okay, so 30,000 episodes, it takes 5 or 6 hours to train.
Oh, okay.
But sometimes, in case most of the episodes, if it is reaching the destination, it can end early also. Terminates early, then it can finish short. So this is how I'm choosing the training points. So the points are chosen randomly from a certain radius 8 to 28 ship lengths, and the ship always starts from the origin with a certain speed of 1 in the with a heading of 90 degrees towards the positive y-axis. So these were the returns and the loss that I got. The returns converge at -200. The loss converges at close to 0. These were the results after the model was trained, waypoint tracking. So the ship starts at origin with a surge speed of 1 with a heading angle 90 degrees. So you can see it reaches all the most destination points in all the quadrants. So since it is able to reach individual destination points, so now we can try tracking a complex path. So this is how it tracks an elliptical path. So it starts from this point, this is 12,0, and it starts with a speed 1 with heading angle 0 degrees, that is oriented towards the positive x-axis and goes anti-clockwise, completes the ellipse. So till now the agent was trained without any external forces.
1 second, Sanjeev, can you go back? So the first time around, I understand that it took a deviation here, correct? It took a deviation from the actual ellipse at the beginning. After that, in the second round, it's able to, the second waypoint, it's able to correct itself and follow the path more closely. So if we ran this for 2 cycles, let's say, which means that we had 1 circle completed, another circle of the ellipse also we wanted to complete, another round of the ellipse also we wanted to complete. So in the second round, would it follow the same path which is shown here, or would it follow a different path through the waypoints?
Yeah, it should follow a different path, because when it reaches this point, at that state, it might have a different velocity. Okay, so it will follow a different path.
Correct. Okay, I would be curious to find out if that is closer to the ellipse or is it further away from the ellipse. Does it lead to a more variation, or does it come to a closer this one?
I'll try it out.
Yeah, you can try it out at a later point.
So
I have a doubt here. Just a
yeah,
second. I'm just trying to understand. So, for example, let's say if I'm starting from any point here on the which is there on the waypoint, right?
Mm.
So, what is the path length between the two waypoints, and is there the dynamics of the system involved in this, or is this the point object you are considering?
yeah. So we trained it with the destination waypoint. So right now, so when it starts from here, this will be the destination waypoint, and once it reaches this point, the next point will become the destination waypoint, and it will try to reach the next point. So it's one point at a time.
No, so generally this, let's say for example, the difference between the two waypoints, the distance, okay, so let's say you are a little bit off from this one, and then it takes some time to reach to, to reach to that, because the dynamics of the system involved in that. So it has its own settling time, and to reach there, right? And then of course as you saw in your zigzag maneuver, it has overshoot as well. So just trying to understand that machine learning takes care of all this stuff.
Yeah, so the dynamics is exactly the same as I discussed. The only thing, the RL agent, it takes a command, it inputs a rudder angle. That's the only input from the agent. The dynamics followed is the same that I discussed.
Okay.
At each time step, the agent learns to take a optimal rudder angle. That's the
Okay, so optimal rudder angle can be anything between -35 to +35.
no, it's not anything. It's a discrete value, so it can be -35, 0, or 35. That's it. The commanded rudder, any three of those values.
Oh, but then in that case, I think it will have some overshoot, because if you deflect your rudder with full 35 deflection, your vehicle will try to move in one direction with full movement,
Yeah,
isn't it?
yeah, you're right. So in DQ1 we can just have a discrete action space. So so next week I'll be trying with with RL algorithms that can have a continuous action space as well. So that should be more practical than this one.
Okay.
No, but I'm sorry, I missed something there. Why is this little less practical? I was lost for a minute there.
So because commanded rudder angle is just one of the three values. So ideally we would want it to be a continuous rudder angle as well.
Okay, but if it is a commanded rudder angle, it still is not as bad.
Yeah, it's not bad because we are limiting the rudder rate here. So
correct. So because you are limiting the rudder rate, and let us say that in case if you followed Avani's suggestion and you were having a model reference tracking, which was based on a second order system, in that case, I would not see the need, or I wouldn't be very sure that if you went for a different continuous action space algorithm, it would really be better. There's no such guarantee is what I feel. Although we'll have to experiment. That is what your research is, and you're going to try that out. But I feel that it should not make much difference, because at the end of the day, you are covering the entire range of the rudder. Only that you have 3 points of control, agreed, but you're still not achieving a, what you call, you still have multiple rudder angles possible all the way between 0 and 35 included in this model. It's only you're only playing around with the commanded rudder angle in this particular case.
yes, sir.
I would suspect that it might not lead to an exceeding performance gain by using a continuous action space, but we'll find out anyway.
Okay. So now I'll talk about how I'm modeling the wind forces. So far we just talked about the performance in still water. So So I'm taking a constant wind speed at an arbitrary direction. So this VW, this will be the non-dimensional wind speed, and this beta will be the heading direction of the wind. So first, so we'll split the wind speed in along the ship frame, along the ship axis. So this will be. So this will be the relative wind speed of the relative wind speed with respect to the ship frame. This will be the relative wind angle that is calculated as tan inverse of V relative by U relative. So this will be the non-dimensional wind forces. So note that all these forces are non-dimensional. That's why non-dimensional is wind force. So the only change in the dynamics is that each x, y, and n will have a component from the wind force. Any doubt here? What the results are. So this is without the presence of wind. So here it has a wind speed of 15. So in this plot, there's a wind speed of 15 at an angle, heading angle minus 90 degrees. So the wind is acting downward. In this plot, the wind is acting. Sorry. Yeah, now here the wind will be towards the left side, so towards the minus x-axis. So you can see the ship is deflected this way. Here, in this plot, the wind is acting downwards. So you can see this. So it is deflected downwards and then somehow tries to reach the destination. And if I include the termination condition, it misses the point. But if I allow it to continue, it just continues and tries to reach the destination, even with the presence of wind.
Now the wind is blowing in which direction in this case?
Yeah, 180 degrees.
So from the top to the bottom?
Yeah, from top to bottom. That's why it is deflected downwards at the beginning and somehow tries to reach the destination.
Okay. Wonder what is happening at the sharp turn. Any ideas from the guild? What might be happening at the sharp turn?
It was going towards the waypoint and suddenly it is changing the direction.
No, I have a feeling that that's because of something else. You see, what might be happening is your heading direction is very close to the wind direction. So the moment you flip over, the yaw acts, yaw force, yaw moment starts acting from the wind in a different direction altogether. That might be causing it. Maybe, I'm not sure. That is something for you to check up on, Sanjeev. Because you see, at this current location where you have plotted it, where the ship is almost heading straight up. Right? The heading angle is straight up. This again is the direction of the wind. And by a small whisker, it's an unstable equilibrium point. It suddenly flips over and tries to come in the beam side the other way around. It was compensating to be on the beam side this way, but then suddenly it tries to flip around. That's what I feel is happening, which is causing your yaw angle to suddenly change. And then the ship has to make this maneuver, roundabout maneuver to reach back the point. But that's surprising. Please come. Yeah, okay. That's what would be my best guess. That's what would be my best guess. Any other thoughts from somebody else? What might be happening there?
So does it have something to do with that exploration, exploitation thing that we discussed? Is it that the rate at which we are doing that is so high that it cannot, explore at the end? Is it something like that?
No, I don't think this is the exploration phase, because by
No,
this time,
this is not the training. Yeah, we are just testing the model that has been trained now, so it has nothing to do.
yeah, because this is not the phase where he's continuing to train. It's a phase where he's testing the model. So, and the presence of the wind is, I think that's what is happening. You see, if it slightly flips further over, the yaw moment starts acting in a different direction. It's like an aerofoil which is oriented to this way versus aerofoil which is oriented the other way. Right? And the lift will suddenly flip from one direction to the other direction once you change the angle of attack. Something like that is happening, which is causing that yaw angle to suddenly shift off, and the ship veers off in a different direction. Okay, all right.
Okay, so now we saw how it reacts to the wind for a single weapon. So now these were the results I obtained when I tried to track the path in the presence of the vessel. So here it starts from origin and it completes this upper circle anti-clockwise and it completes the lower circle. And here there's a constant wind speed acting from left to right.
Okay, left to right is where it is acting. Okay.
Yeah. And if I increase the wind speed above 6 or 7, like it won't be able to track this properly. It will be thrown off.
Okay.
It is starting.
No, come again.
It is starting at the origin, right?
Yeah, it's starting at the origin. It does this upper circle first, goes anti-clockwise and completes the upper circle and then the lower one.
Oh, when it is doing the wind is from the left to the right, correct?
Yes, sir.
The left to the right. Okay. I wonder why the variation is higher on the downside compared to the upper side. Ideally, you should have seen it to be more or less symmetric.
I think that this point and this point, the topmost point and the bottommost point, the wind speed will be exactly opposing the ship motion. Or I think that's why there are more deflections at these 2 points.
Correct. But why one deflection is more than the other is puzzling, isn't it?
Yeah. So at this point, it will be opposing the ship motion. And I think at this point, the ship speed will be in the same direction as the wind.
No, both will be opposing. No, the wind is from left to right. If it takes the anti-clockwise first there.
Yeah, both will be opposing. Yes, sir.
Yeah, both will be opposing. So I wonder why the deflection is more in one case and less in the other. Something for us to take a look at. Okay, all right.
So now tracking an elliptical path with presence of wind again. Here too the wind acts from left to right.
Okay, and here clearly the path is that the top one is having a deviation.
So at this point, opposing.
No, I kind of feel, okay, this is my feeling, that whenever the direction of the heading and the, what you call, the direction of the wind are either 180 degrees, there you will see this problem come. It might be a destabilizing moment. Yeah, okay. We have to look at something called, okay, Sanjeev, remind me next time, we'll look at something called a monk moment, which is generally a destabilizing moment, or it can be a stabilizing moment depending on the geometry of the ship. It's purely coming from a hydrodynamic perspective, but your wind might be causing it to set in this instability, and whether that instability is getting magnified due to the monk moment is what I'm curious to find out. I may be wrong here, but remind me to take a look at that, okay?
Okay, sir. Yeah, those were the results. So this model could be improved by training with the continuous action space, or as Anish suggested, we can use a second order rudder change. And so far these results that we saw, I mean, here while training the model, the wind parameters were not included, so the agent does not know how to react to the, it does not know how to act in the presence of wind speed, and these are purely reactionary. So actually, if we train the model by including the wind speed as one of the operation states, it should be able to perform better under wind forces. Yeah, that's the end of my presentation. Thanks. Any doubts?
All right. Any questions?
I just wanted to ask, when it is tracking that ellipse, it only wants to reach those points, right? One after the other. It doesn't actually want to track the ellipse. It's if we had put those points a little farther away, it wouldn't have gone along the ellipse, right?
Yeah. So if I put the points a little further away, it wouldn't have closely followed the ellipse. Right? It would just try to reach the next point. So yeah, that's right.
So yeah, it's not in essence really a trajectory following. It is actually a waypoint follow. And as long as the waypoints complete the ellipse, it tries to reach one waypoint to the other. But it really doesn't look at the trajectory as a whole and try to make sure that it follows that. That's not the goal of this work. The problem then becomes slightly different, Vallabh, actually. What happens there is, if you have to have a trajectory tracking, then it has to be independent of the path. You have to come up with a methodology such that it's independent of the path. Waypoint is a very simple way to make it independent of the path. You are able to understand what I'm trying to get at?
Yes, sir. If we put the points closer, more number of points along the ellipse, then it would keep tracking the ellipse at a better. It will try to track the ellipse at better.
Actually, we cannot put too many points as well. That would be a problem, because if it is very close, it won't reach the point properly, and the oscillations keep building up. I've tried that, so that is also not.
Oh, okay.
That happens because of a different reason, Vallabh. So let's say that you have a ship and you are having a maximum rudder which you can apply is 35 degrees, let's say. Okay. And when you apply a 35 degrees rudder, the turning radius that it can achieve is about 2.9. Am I right, Sanjeev?
Yeah, 2.9 is turning diameter.
Turning diameter is 2.9. So radius is about 1.5. So if you give a point which is lesser than 1.5 ship lengths away, it is not on the, it's a sharper turn than what it can do, then it will exhibit that what you call oscillatory behavior.
Yeah.
Right. But if the point is sufficiently far away, it gives it a time to react and be able to reach there. So you want the points spaced about, but at the same time you don't want them very far apart. So suppose I had only 4 points on this ellipse, then it's very hard to argue that it will actually track the ellipse. It will actually try to track a rhombus. Right?
Yes, sir. Yes, sir.
But it's somewhere in between the answer lies, that you won't want too many points, at the same time you don't want too few points, or you don't want points which are too close by also, which may cause more problems.
Yes, sir.
And that's kind of coming in because this one is low. The idea there being that the reaction time of these vessels is low. And it takes a while after I decide to go one way for me to actually start heading in that direction, because they are sluggish systems in some sense. Okay. Any other queries, comments, or suggestions? I've not heard our new members talk at all. I'd be happy if our new members could give out some suggestions or comments. Aradhya, Mansi.
Yes, sir.
Hi, am I audible?
Yeah.
Yeah, I think I'm just still taking in, but I think it was a very fruitful discussion. There were a lot of points where I was missing out on what could a possible question be, or if things are not clear to me. So I think overall, like in the last 1.5 hours, I got to learn a lot about how even RL is helping out, and like how the first and the second order systems would have different kinds of things coming into play, even in terms of selecting what kind of RL model you want to run around. So I think overall a very good presentation. Not a lot of suggestions from my end, but yeah, I think some of the things during the presentation were that I was actually looking for the legends a lot of times during when I was reading graphs, because I didn't have a full understanding of what you're trying to do. So sometimes maybe just elaborating more on graphs would help, because when I'm reading, I want to understand fully like what I'm seeing on the screen. So that's a very minor suggestion that I have from my end.
Yeah, point taken. Yeah, thanks.
Hello.
Yeah.
Am I
Yes,
audible?
Aradhya, go ahead.
So, I found the presentation interesting, but I was reading sideways also something about your activation function. As you said, you have tried using ReLU as well as other activation functions, and you finally decided to go ahead with TANH.
Yeah.
But since we are seeing different anomalies here, I was thinking whether you can give a try to max out units. Somehow we can try to learn our own activation function in this case. Is it possible?
To learn out different activation functions?
Yeah, we can use max out units, right?
Sorry, come again. Max out what?
Max out network for learning different activation function.
Max out network for trying out different activation functions.
Yes.
Okay. All right. Can you describe it a little bit more? Because I am not familiar with what you're talking about. Maybe enlighten me a little bit.
It's like a activation function. It says the activation function is a max of the input. Like I was also reading that
Oh,
paper itself. So
max of the
right,
inputs.
yeah, right now I cannot comment entirely on that.
Okay. I was thinking this is some other functionality. Okay, you just want to take the maximum of the inputs which are coming in and pass that down to the next level. That's
It would be like okay.
Is that what you mean by max out? That you take the maximum value of all the inputs which is coming in, and that becomes the output of the node, each node?
Yeah, sort of.
Okay. Any
Because it tends
particular?
to work. It tends to work well with the convolution of the network. Whenever you have, whenever you are trying to regularize it, trying to control the stuff such that it will give you an output you desire more. So I'm not very sure whether it will work entirely with a reinforcement learning network or problem, but yeah, that's what I'm reading sideways.
Okay, that might be an interesting thought. Maybe if you can look at it a little more closely and come back and have a discussion with Sanjeev, if you find that that is indeed interesting enough and can have a potential application, I think that would be a good idea to have a discussion with Sanjeev, and we may be able to incorporate it if really that's the case. Although I'm not still following, if it's the maximum value of the node, why should that be better? I
Like
can't think on the top of the head, yeah, but maybe requires some thought. Okay.
Also, apart from that, one thing that I didn't understood is about how you're back propagating. Like, since all these, for example, if you're talking about rewards, if you go left, suppose you give a reward of 1. If you go right, you give a reward of -1. Since these values are discrete, how are you back propagating? Like, maybe a lame question. I don't know.
Yeah, so yeah, this is the loss function for AQN. So from here, using this loss function, back propagation is done. So right now the batch size is 1. So after each episode, 1 update is done. I explain how the updates are done. So take multiple samples from the replay buffer for updating.
No, I think what he's asking is your reward discrete?
No, it's continuous. It showed the reward. It's not discrete.
Correct. So since the reward is not discrete, it is not, it really doesn't conform. Your question is kind of slightly off the mark there, because the reward is actually continuous. So the loss function is continuous and differentiable, and you can actually propagate the gradients back. Did that answer your question?
Can you go to the rewards first? Rewards function. Oh, okay. Yeah.
These two rewards only are plotted here. Rounded to 1.
Only the action is discrete. The reward is continuous. The state is also continuous. Only the actions that you can take is discrete. Should I take plus 35? Should I take minus 35? Or should I take 0? Those are the only 3 discrete actions that you can choose from. But the expected value of the reward which you will get, that's not a discrete value.
Okay.
Yes, Avanish?
Hi. Quite interesting work, ma'am. Very interesting. So, you know what I would be interested in looking at your actions plot. If you can show me your actions plot, which goes minus 35, 0, plus 35. And let's say, for example, if someone applied the same other action to the dynamics of the model, the MMG model, and see if it does the same thing.
I didn't follow that. No, I didn't get your point. Can you repeat again?
It's quite interesting to see that it follows that ellipse or the circle. Okay. So let's say, for example, if you plot the actions, the rudder actions for that circle, and if I take the same rudder action and if I apply to the dynamics of the system, I mean the mathematical model, and then I want to see if it tracks same way.
Yeah, underneath the hood, what is running is the mathematical model. Mathematical model is what is running the simulation.
Okay.
So it is the MMG model which is running at the background.
Oh, okay. Yeah, it's quite difficult to understand. Okay. So in background, the mathematics runs the nonlinear dynamics, and then your other action will be based on your machine learning algorithm, and then you apply it to the nonlinear system.
So at each time step, these observation states, these values are calculated and input to the agent, and it outputs an action space. I mean, an action rudder angle from a command rudder angle among these 3 values. That's it. And the dynamics is what is running the system.
And these values of the observation state that you're looking, these observation state values, they are actually coming from your MMG model.
Okay.
So you calculate the state value.
So yeah,
go ahead.
So I think that it looks like quite energy efficient as such. For example, you are right now it's 3 points, but let's say if you are doing some path follow on the track, then it will be showing always the 0, so no rudder action, right?
Yeah, correct. So if you are actually on the path,
quite energy efficient.
You think it will be more energy efficient?
Yes. So
okay, I didn't follow that. Why would it be more energy efficient?
So that there won't be more of rudder action involved, and so for example, let's say for I am deviated little bit, let's say 1 degree, 2 degrees.
Yeah, if you're only deviated by 1 or 2 degrees, it will not take a rudder action.
Yes, so it will be like more or less like not doing anything, and it will be more of energy efficient. I mean, that's my
I actually, yeah, but I have a feeling that that might not be so true in the ellipse case with the wind. Can you go to that, Sanjeev? Clearly, that place, this technique has failed, right? It is no, it could have maintained course much better, probably if it were heading straight without having to worry about the rudder action. But then, in all fairness, it's probably the sway, the yaw angle, the yaw force due to the wind, the yaw moment due to the wind, which is pushing it on this side and that side, and it's trying to compensate and get back. We have to see at this case though. Sanjeev, I'm very excited about this. There might be a potential instability that we are dealing with here.
Okay.
See, that's what I'm trying to get at. Here it is trying to compensate, but the wind is too strong. See, even if it wanted to maintain the course, it is unable to maintain the course, right?
Yeah, but it's sort of trying to reach to the force, right? I mean, so it started deviating, let's say, at 5 and 10. And then at that point of time, let's say it is exactly, so this side it's left to right, so it means it will be 180 degrees of the way. Oh,
correct. At the top it is 180 degrees, and that's what is causing the problem. Because as it oscillates on that loop, the yaw moment will act in one direction, and the next second, once it crosses, its yaw angle becomes negative, it will act in the other direction. So it's a flipping yaw moment.
Or maybe probably making that 180 degree minus 180 degree that thing, the Euler angle is the gimbal lock.
No, this is not gimbal lock, because there is only one angle here.
So
this is a 3 degree of simulation.
So let's say so I'm trying to understand this. Let's say for example we have the psi error, right? So here let's say the psi error, and then if your relative angle between the wind and your ship is 180 degrees.
It's flipping between minus 180 and 180. That's what you're saying, right?
Let me see somewhere if it goes minus 0.
The question is that if it is flipping between a large value, like there is a switching type of a thing which is happening. But I don't think that is happening, because I think Rohit had taken care of that to my knowledge.
Okay.
Maybe Sanjeev has to check up upon it once. What is happening to the course angle error? Is that what is destabilizing it? Is it flipping between minus 180 and 180 or some particular value? Because see, 180 and minus 180 represent the same angle. But let's say that I am 180 minus 5 degrees and 180 plus 5 degrees, then the angle will actually be, the course angle error, is it observing a jump? Is it 175 degrees, and the next moment it is becoming minus 175 degrees?
Sir, I don't think that should affect, because the reward function is symmetric.
The reward function is symmetric. No, that will affect, because that will affect. Reason being that you're trying to compensate in one direction, and suddenly the next moment you're trying to compensate in the other direction. Okay, so what I'm trying to say is, let's say the ship is like this, okay? It's being swayed this way, then it has to compensate to try to come this way, correct? Similarly, if it is swaying this, it's yawing this way, then it's trying to compensate to come back onto the straight track to move this way. But if your course angle errors is observing a flip, then what is happening when it is like this? It's trying to do this, but when it's like this, it's trying to bring it back like this. Then you will see a big difference in the scenario. Whether that is happening will be dictated by whether your course angle error is observing a switch. That might explain this.
Yes, sir. We should plot the course angle error and verify that.
we should plot the course angle error over time for that trajectory and verify what is happening. Whether you're seeing a flip in the angle. Is it flipping from -180 to 180 when that jump is happening? Is that jump happening? But to my knowledge, Rohit fixed it. But let's check upon it one more time.
Yes, sir.
All right. Any other questions?
Sir, in this, it was not trained to take into account wind, right?
No,
Yeah.
it was.
Yeah, in the training process, it was not taking into account the wind.
So it is, in case of winds, it is purely based on its reaction to the current state.
Yeah, that's it. So we should try including the wind force, the wind speed and the direction as one of the parameters. That should definitely improve the performance of wind forces.
So there will be more observations?
No, I disagree. I disagree that we should put the wind as an observation into it. Yeah, if you really are able to measure it, then yes. But for most of our applications, we won't be able to measure it.
Like it could learn that wind is there, like because of its states.
Yeah, that would be a feed-forward control if we could measure wind and give it to it. Correct. But unfortunately, I don't.
I'm not sure, but it would during its learning, if wind is there, so it would from what its trajectory is going on, it might learn that wind is there, and it is supposed to react in some general way to when wind is there.
Yes, that's what I mean. It will react in a feed-forward way, which means that even before the wind actually affects your trajectory, it takes a preactive measure to account for the wind.
Yeah.
Right? If you give wind as an input to it, it should be able to do that. That's the primary thought process. Am I right? Yes, and I see that that's definitely a possibility. And that might have prevented ever given to happen? Question mark.
Sir, and why wind cannot be added to the observation state? Like, we can train it on...
The reason why I don't... Yeah, you can train it. I mean, it will be a good simulated study. But for me to be able to make this as an experiment will be much harder, because then I'll have to generate wind in a reliable manner for those experiments, which I currently don't have the facility for that, isn't it?
Yes, but in open environment, like, it is possible, right? Wind can flow from any direction. So
it can flow from any direction, correct? But it will not. Okay, you need to be able to account for these winds which are very strong. So which means when you are simulating or when I'm experimenting with reinforcement learning, my model should be experienced to the data. I have to provide that experience to the model. And I can't guarantee that in the lake, no? I can't guarantee that there will be a wind speed of so-and-so on so-and-so day or so-and-so time when I'm testing.
Yes.
Only if I give it the information, it can learn. It can't learn what I don't provide.
Yes.
Isn't it? But yes, if suppose I had a wave basin where I had a proper wind facility as well, where I could generate wind in multiple directions, then this would be a very lucrative process to try to study.
Yes, sir. Yes.
So we need more facilities. Always the case. All right. Any other thoughts? Okay, let me stop recording.